Adhesion is a Ruby framework for building voice applications. If you've ever built like a web application, use Ruby on Rails or something like that, Adhesion is that, but for telephone, for voice applications. So anyway, pretty cool. But that's not what this talk is about. This talk is all about Asterisk, because we're at AstriCon. And one question that I see over and over, and it always makes me cringe just a little bit, is, but does it scale? And the answer to that is yes, probably. And that's what we're going to talk about. So let's talk about what we're going to talk about. Here's the agenda. So we'll talk first about some of the terminology, some basic terms that'll be helpful to understand as we discuss scaling. Then we'll look at some of the tools of the trade, the things that I use to measure Asterisk's performance. I'll look a little bit at the methodology. And then at the end, the actual inspiration for this talk was trying to figure out a way to communicate how Asterisk scales, and perhaps more importantly, what design decisions you make impact Asterisk scalability. So we'll get to that at the end. So first, let's talk very quickly about terminology. There are two main things that you probably care about: calls per second and concurrent calls. So I'll explain each one of those. Calls per second, pretty straightforward. It's the rate at which new calls are started. So if you're dealing with 5 CPS, then every second you're getting 5 additional new calls being set up. Primarily, this is meaningful to people where the average call duration is very short. So think dialers, where the line may not even be answered, right? That's a very common case where you need a high CPS. The other possibility is where you're not actually touching the media, where it's just a proxy. You're basically setting up the call and passing it back to Asterisk, and maybe you're fronting a lot of Asterisk boxes. So in that case, you would need to be able to handle high CPS. And I don't need to take away from this because it's an important metric, but I think people tend to get a little fixated on it. And I think for most people, this is not the bottleneck. For most people, I think, in this room at least, concurrent calls is probably what you're more interested in. This is the number of calls active at any particular time. And I think this is what people really mostly care about when they're scaling Asterisk. Let me kind of explain how these two things relate. So forgive me, this is the only time I'm going to actually use math, I promise. CPS, calls per second, times your expected or your average call duration is how you arrive at your peak concurrent calls. This is an interesting relationship. So let's say we have 5 calls per second and our average call is 30 seconds long. We can extrapolate that after about 30 seconds, we'll have 150 calls active on the server, right? Pretty straightforward. And it's also, logically, it follows that if you double the number of calls you're setting up every second to 10, that you're going to end up with 300 concurrent calls. What's a little bit less intuitive, although the math still bears me out, is that if you double the length, simply the duration of the call, you're also going to have a corresponding increase in your concurrent calls. And in a lot of cases, the limiting factor isn't how quickly you can set up and tear down calls, but it's how many concurrent calls you're handling, especially if you're touching the media. All right, so that's enough of the math. I want to talk about the tools of the trade. These are the tools that I use to generate load, to measure Asterisk, and these are tools you can use. These are all open source. All right, SIPPY. I'm going to ask an inverted question. Has anyone not heard of SIPPY? Okay, a handful of you, all right. So SIPPY is pretty much the open source tool for generating load. It's been around forever. It's actually still under active development. I think it's changed maintainers recently. The code's on GitHub now instead of SourceForge. But really, when you talk open source load testing tools for SIP, really SIPPY is where it's at. It's very, very high performance. You can take a moderate machine and it will spit out enough SIP traffic to swamp just about any Asterisk box you can find. It's also very, very flexible. Its flexibility comes in large part from this XML-based configuration. When you generate a SIPPY load test, what you've got is an XML document that contains all of the requests and responses that what you send to the server and then what you expect to get back. It also comes with a rather large number of somewhat awkward command line options. And oh, wait, did I mention that it's very flexible? Well, all that flexibility is you can test any SIP scenario you can imagine. Especially, it's very easy to create broken SIP scenarios where you accidentally send too many invites or you have your headers out of whack. And there are cases where that's a valuable test, right? There are times where you might want to test a proxy for compliance with some oddball configuration. The problem is that I think for most people, those oddball configurations aren't terribly helpful, right? For most of us, we just want to spin up calls and see how the system behaves. And dealing with having to figure out the right headers to get that done is kind of the problem. So I'm just going to kind of walk you through what happens if you wanted to create a load test with SIPPY. First, and the screen's a bit washed out, so I apologize for that. First, what you need to do is basically write a SIP interaction. And this is SIPPY XML here. And I'm just going to kind of show you, this is a pretty simple call, but it's kind of a lot to write. And this is a call a number, wait 30 seconds, and hang up. I mean, it's really, actually I think it does send some digits in the middle, but it's really not very complex. But you saw how much code that is to write and how much it is to debug. Step 2, especially if you're testing anything interactive, is you need to actually call into the system you're about to test, and you need to record a call. So for example, if you're going to call into an IVR, you actually have to call the number and press a digit, wait for the next prompt to come up and press a digit, and you actually have to capture that with something like TCP dump, because SIPPY is going to use that TCP dump to replay against the IVR when you actually start the load test. And really the only efficient way to capture that is to actually call the system and record it. The next thing you have to do is decide the arguments you need to use for the load test. This is a load test I ran the other day, and it's got a lot of options, which is good. That's the flexibility, but it's got a lot of options. And I actually can't tell you all of these. I have to go look at the documentation every time. Anyway, and the step 4 is, of course, test and hope it works. And if it doesn't work, then you've kind of got to go back and figure out where you went off the rails. Was it, you have a bad header? Was it because your PCAP's in the wrong audio format? Was it because, I don't know, lots of things that can go wrong. Now take that process that you've just done, and you've basically covered one path through your IVR. Now you have to do all that again for all the other paths. So it's not very efficient. It's a great tool. I mean, it really does do a great job of generating load, but it's cumbersome. So the problem with SIPPY is time. You end up spending a lot of time building tests. And what this translates to is people don't build tests as much as they should because it's too much work. So I got really annoyed with that. And I created a project called SIPPY Cup. So SIPPY Cup it's open source. It's on GitHub. And by the way, I'll have all the links to all of these things at the end of the presentation. So don't worry about that. We'll put them up. But the tagline there, which you actually can't see, is it's create SIP load tests the easy way. Now SIPPY Cup isn't designed to do everything SIPP can do. But it is designed to capture the common cases, right? Where you need to just call into a system, maybe play back some digits and hang up, and then do that 1,000,000 times so you can test your system. That's what SIPPY Cup is designed to do. So you have basically 3 steps to create a SIPPY Cup test. Step 1, write the test in a simple syntax. And I'll show you that syntax in just a second. Step 2 is SIPPY Cup will actually compile the steps you write into the SIPPY XML and PCAP. So for example, I talked about when you call into the IVR and you have to navigate through the menus. What SIPPY Cup will actually do is you tell it what digits you want to press and at what intervals. Like, after 3 seconds, send these digits, and after 6 seconds, send these digits. It will actually go create a PCAP file for you with audio at the right spacing and with DTMF digits at the right spacing. So changing a test is a matter of simply changing the SIPPY Cup syntax and then recompiling. So you can easily debug and adjust your tests. The third thing that SIPPY Cup will do for you is it will run SIPP for you. It will actually figure out the right arguments and pass them to SIPP so you don't have to remember them. So I want to make this really clear. The first couple steps I showed you with all that XML floating by and the really long SIPP arguments, both of those things are fully contained right here. This is a complete SIPPY Cup test scenario. You have your source and destination. I've got a pointer, I can use it. You've got a source and destination. You've got the maximum number of concurrent calls that you want to use. You have the calls per second. So we're going to be setting up 5 new calls every second. The total number of calls to make. So depending on how long that call lasts, you're going to keep calling until you've made 20,000 total calls. And then you have the steps. And these are pretty straightforward if you're familiar with SIP. Send an invite, right? Just start the call, basically. You're going to wait for the far end to answer, sleep 3 seconds, and then we'll send these digits, 404, 555, 1234. We'll sleep another 5 seconds, send a pound maybe to confirm that we've entered the right telephone number, and then wait for a hang up. Now, if I needed to change these digits, like I wanted to test a different phone number, or if I needed to add a step in between, if I were doing it the old way, I'd have to change to the XML and re-record the audio. With this, I just change the instructions, recompile, and go. So the time to create a single test or a single path through my IVR with SIPPY alone might be like an hour. And this is after I've learned SIPPY, right? I mean, it just takes time to kind of fiddle with it. But with SIPPY Cup, I can do it in about a minute. So the upshot of that is this is kind of a game changer for us. We can actually test many more scenarios much more rapidly because we can build these tests so much faster. So there's one other tool I want to share with you. This is another one. This is called SIP Treadmill. This tool was actually, we worked with AT&T Foundry in Palo Alto to build this tool. They wanted to do some testing of some large IMS infrastructure, and we needed something that could generate the load and look at the reports and then compare the reports over time. Basically, as they made adjustments to the system, we wanted to look back historically and see how we had done. So we worked with them to build a web-based, basically a front end to SIPPY. Now, because we had also been working on SIPPY Cup, we added support for SIPPY Cup. So you can actually write your scenarios in either format, in the simplified SIPPY format, or if you need something more sophisticated that SIPPY Cup doesn't handle, you can also put SIPPY right into it. But this is a little bit of what it looks like. And I apologize, that is pretty washed out. But what it shows you is on the left here, there's a box that kind of illustrates the parameters of the test. It shows you which system was tested, the IP address of it, how many calls were sent. There are links to download the raw error reports and the raw statistics. So if you want to do additional processing in your own tool later, you can. And we also generate some nice graphs. You can see right here, the yellow calls are calls that have been started. The green calls are calls that completed successfully. And you can see they're ramping up over time until we hit saturation and the red appears. And the red is bad. The red is failed calls. So our capacity of the system is basically this point here where it stopped working. Another graph, which you totally can't see because it's washed out, is there's a line right here that shows the number of concurrent calls that we generated over time. So you can actually see the ramping up of the system. And it's kind of cool. There's a little wiggly line at the end where it started to break, which I think is cool, but you can't see it. Ask me for the slides later. I'll be happy to, I'll tweet them out or something. The other thing we do, which is really cool, is we capture invisible things. We capture jitter, packet loss, and CPU and memory utilization on the target. So this is not foolproof, but it does give us a pretty good indicator of the perceived call quality. What you can see, there are actually two lines here. There's this baseline. This is the average jitter. The more dramatic one is the peak jitter, which is kind of flat at the beginning, but then it really starts to get wobbly up here. And what that's a symptom of is the system becoming saturated and not being able to process calls anymore. And the result of that is there's delay sending out audio. So from the caller's perspective, your audio quality has just fallen off. And we have a graph as part of Treadmill that will indicate that. We also show packet loss and then the target resources. So down here you can see the CPU utilization climbing as the number of calls active on the system climbed until it basically fell over. And then there's also a line right here that shows memory. We're going to pick darker colors next time. Okay, so those are the tools, SIPPY, SIPPY Cup, and SIP Treadmill. The next thing I want to talk about is testing methodology. And this is going to be a little bit sort of general methodology and a little bit what I used for the results that I'm going to show in just a minute. One thing I want to reinforce is that there are bad questions and good questions. There are ways to think about the capacity of your system, and they have a lot to do with what you're doing. So bad questions might be something vague like, how many calls can Asterisk handle? I don't know, a lot. I mean, it depends on what you're doing. I heard doing X is faster than doing Y. Well, where did you hear that? What were they doing? Have you tested it? Can you back it up? How much CPU or memory do I need for this? Man, I don't know. Are you talking to a database? Are you transcoding? Are you conferencing? What are you doing? And then, yeah, my favorite. But does it scale? Yeah, get that a lot. Okay, so good questions. So good questions are, well, what is my average call duration? How long are my calls going to be alive? That 30-second example I gave you, I imagine for a lot of people, 30 seconds is kind of a low average. Depends on, are you a call center? Are you a calling card operator? Are you an ITSP? I mean, the answers to those questions and the answer to what is my average call duration will be very different depending on your use case. Another question to ask is, am I touching the media? For a lot of people, if you just have a proxy, you're just setting up the call and passing it to the far end, you're not touching the media. So what you care about is very quick call setups and then get out of the way. And that's a different load profile than staying in the middle of the call. What happens if I enable recording? Really, how much will that eat into my expected capacity? Can I optimize out transcoding, assuming you're transcoding in the first place? And transcoding might be in the form of taking GSM on this side and ULAW on this side, or it might be in the form of ULAW on both sides, but your audio prompts in the middle are in wave format, right? So there are different places you might be transcoding. And can you get rid of that? And then do I need mixing or conferencing? So a lot of times when we'll implement call center software, we'll have to use, basically we'll park the agents in a mixer and leave them there until a call comes in. And then, is that optimal? Is there a better way to do that? Or really, is that even my bottleneck? And again, I won't know the answer until I test. So what I want you to take from this is, or I'm sorry, what these questions inspired me to is to ask the question, what does each asterisk feature, what is the impact of each asterisk feature on the capacity of a given system? How much does recording cost? How much does file playback cost? How much does transcoding cost? And I came up with some pretty interesting results. I'll get to there in just a second. I want to mention sort of the QUADUMVIRATE, if you will. I don't know if I made that word up, but it sounds cool. When you're looking at a system, there are four main things you really want to look at: CPU, memory, disk, and network. Disk and network are both I/O, and for my purposes, I was really interested in Asterisk's performance, so I kind of didn't focus on those. Those are very important things, especially if you're in a bandwidth-constrained environment, but that wasn't part of my testing. That would not have ruled out Asterisk's capabilities. So I really focused on CPU and memory for my tests. But I do want to mention, keep these in mind. They're important factors. Okay, so that takes us to the results. So I'll say up front that I did not exhaustively test every permutation of things, because I would still be testing if that were the case. But I picked a few things that I felt like were interesting. I picked some results. I did focus on things where I felt like Asterisk would be the bottleneck at some point. I'm also going to point out that I intentionally don't have hard numbers in this presentation. And I did that intentionally because my system is different than your system. This particular box probably doesn't look a lot like the boxes you have in production. I mean, it's generic enough that it's representative in terms of percentages. But I don't want to make any wild claim that Asterisk can support 10,000 calls, because I don't really know that. But what I can tell you is, once I've baselined it, what was the impact? In other words, what percentage of call capacity did I lose after turning on some feature? And that's what I want to focus on here. So this is our baseline. What you can see from the baseline is we started with a bunch of calls and slowly increased them until we got to the point, you can see kind of a drop off here, and these red calls showing up a few seconds later, that's where they started to fail. So basically the part where the last time where it was stable, an average of this point right here, that was what I considered the peak capacity, because beyond that point, we started getting unacceptable loss. Now you can see that Asterisk actually kind of soldiered on pretty well, and a lot of that green toward the end is still working calls, so it didn't just fall over. But the red is bad customer caller experience. You don't want that. So we called that the capacity of the system. Man, I'm disappointed this line is missing. But what you can see here is the calls per second ramping up to about here, and then the line gets really wiggly. Again, just because Asterisk is basically handling some calls and dropping others, and so it's porpoising. The other thing, yeah, and actually what's really cool about this is you can see a pretty strong correlation between the time where we hit peak capacity and the time where Asterisk hit 100% CPU. And that's kind of your smoking gun that this particular test was CPU constrained. We were bottlenecked on the processor. How did I measure CPU? We used, I think it was VMstat to capture the output. And there was nothing else running in the box, so basically it was all Asterisk. Right, and you can't see memory, although in this test it's nice and flat. It's somewhere down here in the 20% mark. It really doesn't grow. This baseline test was a back-to-back user agent. So basically I called in on one channel, Asterisk turns around and calls right back out. It does handle the media, so it was can reinvite equals no, basically, right? The media was still flowing through Asterisk. It was not transcoding, so I figured that was kind of a nice baseline test. And you can see that saturation point I talked about. So the next thing I did was I looked at file playback, just native file playback. So in this case, the caller calls in, and instead of being connected to another party on the far end, we actually read an audio file from disk and play it to the caller. In this case, the audio file is in a native format, so there's no transcoding. And you can kind of see the saturation points over here. Now, this graph and every graph from this point on have the same volume of calls, so they'll be comparable on a time scale. The previous one, because the back-to-back user agent had extra capacity, I had to start at a higher number. You'll see what I mean in a second. The calls per second basically climbs just like the total calls, and it kind of peaks out about here, about the same point. On this one, yeah, you can't see it. Again, the jitter starts off nice and flat, and then it gets really wild as we saturate. You can kind of see it here in the average, but the peaks are way up here, actually. And of course, we have another nice, very clear correlation with CPU. We were definitely CPU bound on this test as well. Memory is, again, you can kind of see it right here, right? That little line, that actually carries all the way across. It's very flat. So now what happens if we transcode? Same basic profile. You can see, I think we started to bottleneck a little bit earlier here. You can just see a little hint of red sneaking in. The calls per second profile is very similar. Jitter, kind of the same story again, that the peaks are way up here. So you've got a lot of variability. You're probably going to have some stutter in that audio. And again, target resources, pretty clear correlation. Hit peak CPU, start dropping calls. The next thing I did was I actually tried two different kinds of conferencing. The first was every time a caller would call in, it would be randomly assigned to one of, I think, 100 conference rooms. And at the peak of the test, I saw something like 10 calls per conference room, although that's not an exact number. But you can see we peaked out even a little bit earlier now. And jitter, again, the same story. It's actually back over here where it's starting to peak out. And CPU. Now, I did do one other test, but I didn't include results for it. I'll mention it very briefly. I hit some kind of, I'm not sure what it is. I think it's actually a bug in Asterisk. I tried basically putting all of the calls into a single conference room, and I actually feel bad for the server because it must have cried at that. That just had to hurt. Unfortunately, it left Asterisk in a not entirely functional state. So I can't draw any conclusions from it other than to say, if you're running very large conferences, be careful for now. That's all I can say. And it'll get fixed, I'm sure. We'll present maybe the findings next year. This one I think is also even more interesting. So this one basically is still the same kind of call profile, but we enabled recording. And you can see pretty early on, we saturated out, and then, I mean, look at all those failed calls. So once we hit that point, it was pretty much all bets are off. I think what's different about this test that's surprising, and you're not going to see it, so I'm going to have to draw it for you, but the CPU grew as predicted, as we've seen in every other test. But what's different about this one, right here, there's a memory line. So on the recorded calls test, not only did we saturate the CPU, we used all the memory on the box. And this is the only test that did that, which I find very interesting. And I haven't totally figured out what's consuming all the memory. I can say that after the test, the memory did drop off. So it seems to be maybe something, maybe SOCs having to process all those calls. Whatever the case was, this was not simply CPU. So I actually was surprised by that. I did not expect to see that. So here's the results. Our baseline is at about, call that 100%, right? That's the max capacity of the system, the highest number that I observed in any of the tests. By just doing a native file playback, we lost about 25% capacity. And I don't know, maybe lost isn't the right word, right? The system had 25% less capacity due to this additional requirement we put upon it. Transcoding, actually, this second column here, had less of an impact than I thought. I kind of thought transcoding would be harder. Now, this is transcoding to a file, right? So maybe their Asterisk caches it. I don't really know. What I can say is that it wasn't that much worse than regular file playback. The split conference was a bit more of a hit. You can see it's down to 66%. So you have a bunch of conference rooms with a handful of people in each room, and they're all talking to each other. And then, yeah, the big one, almost 50%, or over 50%, reduced capacity from recording. So that's an expensive operation. Now, one thing, there are many more things I could look at here. I used the default. It probably was recording in wave, which means really it's also transcoding. So this probably could be optimized. But again, I'm going to encourage you to test for yourself and figure out what works there. But these are the results that I saw on my system. So if you hear nothing else today, If you take nothing else out of this room, please take at least this home with you. Test for yourself. And I'm hopeful that the open source tools that I've introduced to you today will make this a lot easier, that everybody can test, everybody should be testing, and that reading it from some guy on the internet is probably not the best source of information. Seems like you've heard this before. So SIPPY Cup, SIP Treadmill, SIPPY, these are all open source. And let me actually get you to some references. So sippy.sourceforge.net, the SF works as well. That's the basic tool that powers everything else. SIPPY Cup is on GitHub, modulingo.github.com/SIPPYCup. There's some documentation on how to use it. I would say SIPPY Cup is pretty mature at this point. We've used it pretty heavily. SIP Treadmill is useful at this point, but I will say it's also still under development. Obviously, as open source, we welcome contributions. But it does produce pretty graphs, so I had to include it because it really makes the presentation nice. Also open source, and it's under the AT&T repository since that was their project to begin with. And I'm Ben Klang. Feel free to email me, tweet me if you have questions. I'd love talking about this stuff. But at this point, if you have any questions now, I would love to hear them. Hang on one second, the mic's coming.
Did you try using the SIPPY Cup tools for outbound calls, for originated calls from Asterisk?
Outbound from Asterisk?
Yeah.
Only in the hairpin calls, right? So the calls that would go into Asterisk, Asterisk would then dial to another SIPPY instance.
Yes.
So did I test only outbound calls? No, but you could. So in treadmill terminology, we have a sender scenario and a receiver scenario, and you can use them separately if you like. But you can write a SIPPY test that waits for an incoming call. If you look at the SIPPY Cup documentation, it talks about there's an instruction, wait for an incoming call.
How about treadmill? Can it receive calls?
Yes, yeah, I can.
And do the same analysis and everything?
Yep, yep. I'll admit that's newer, so there may be bugs. I haven't tested as much. But if you find a bug, report it, and we'll work on it.
We'll make it tested.
Okay.
Question. Did you test the Asterisk directly on a hardware machine or on a virtual environment?
I'm sorry, I didn't totally understand the question.
So did you test, the Asterisk that did you test about the results? It was compiled and running directly on a hardware machine?
It was on another machine. So both machines were on a LAN. I didn't want the load from SIPPY to alter the behavior of the Asterisk system, right? So they were on they're on two separate physical machines, not virtualized.
No virtualized.
No virtualized. And I should probably also add, this was Asterisk 11. I wanted the latest LTS. I didn't feel like it was fair to test 13. There may still be bugs. I didn't want to have those show up. So I picked the latest LTS. So it's 11.13, I believe, is what I tested.
On your recording test, did you happen to do any tracking on the system I/O performance at that point? Because one thing we've noticed, we do heavy recording, and that's usually when we start running into performance issues, and specifically pegging the CPU, it's always in I/O
Disk
wait.
I/O, yeah.
So
I don't yet have that. I would like to have that. It would be a really nice thing to add. Unfortunately, I don't have that data. But I agree with you. That would probably be very interesting, specifically for the recording scenario, because really you can't cache that, right? Each call is going to have its own recording.
Yeah, unless you put your bar spool Asterisk in some sort of RAM disk. But
and we've done that before, record to RAM, then move it later. I mean, there are different kind of tricks you can do for that. But unfortunately, I don't have numbers for it right now.
Someone else? Okay. Any other questions? I guess not. Thank you, Ben, so much.
Oh,
That was
thank
great.
you.